So welcome back. Just to kind of remind you where we are, we're at part 2 of lecture 7. And what we're trying to do is we're trying to prove this following theorem, namely that you have a basis if and only if everything can be expressed uniquely in terms of that basis. And before the break, I proved one direction, that if we have a basis, then you can express everything uniquely. And now what we want to do is finish up this proof and show that if V1 through Vm has this uniqueness property, then we in fact have a basis. Okay? So let's go over to the beginning of this proof right over here. So let's take some V in sort of our vector space. And now our goal, right, is to show that V1 through Vm is both linearly independent and it spans. Now, we take a vector V inside of V, and we were given that V can be written as a linear combination. And in fact, we're given that it can be written uniquely in terms of VI's, but we don't need the unique part right here. So since V1 through V can be written as a linear combination for some AI inside of F. So really that means that V is inside of the span of V1 through Vm. So this implies that V is the span of V1 through Vm. So V1 through Vm is a spanning set, or a spanning set of V. Okay, so our vectors V1 through Vm satisfy the first property, that they're a spanning set. Next, we have to show that they're linearly independent. And so let's consider the zero vector inside of V. Well, since the zero vector can be written as 0 times V1 plus 0 times V2 and so on. We have one way of writing the zero vector, but we're also given that this is the only way. But since this is the only way to write 0 as a linear combination, because we're given that anytime we write a vector, it can, in terms of V1 and Vn, you can only do it one way. So since this is the only way to write 0 as a linear combination, this means that the vectors are linearly independent. Then V1 through Vm, linearly independent. So we have that our set of m vectors is both linearly independent and a spanning set. So V1 through Vm is a basis. I have just enough room there to finish off the proof. Okay, so that proves one kind of a useful fact about checking whether something is a basis, and it's a useful property when you're trying to prove things. Okay, so now we get to kind of one of the two kind of very important theorems that we're going to talk about in today's lecture. So the first one says that if you start with a spanning set, you can keep removing vectors from your spanning set until you get a basis. Okay, so I've called this theorem spanning set to basis. And it says every spanning list of vectors can be reduced to a basis of V. So this is great if somebody says, here's a collection of vectors that spans your vector space. You can start removing vectors in a particular order until what you're left over with is a basis for V. And here's how the proof goes. Suppose that we know our vector space is spanned by V1 through Vm. And so let B be our initial list of vectors. And what we're going to do is, first of all, we want to remove any VI that's 0. Because in some sense, if there are any 0 vectors in here, they're not really contributing to what we need. So in particular, we're going to relabel. So we're going to assume that the first L of them aren't 0, but the last L of them, the last L, well, that should be L plus 1, from L plus 1 to M is 0. So basically, we're going to wipe out all the zeros because the spanning set of V1 through Vm is still going to be the spanning set of V1 through VL. These 0 vectors don't really contribute to the spanning set. So as the first step, we've eliminated all the 0 vectors from my basis, or my possible basis. Okay, and now what we want to do is for each of the vectors that are left over, what we want to do is kind of check to see whether we need it or not. Now, V1 is not 0, so we want to definitely keep V1 around. And now we want to look at each of the next ones. Okay, so from J going from 2 to L, if Vj is in the span of V1 through Vj minus 1, right, we can remove it. We can remove this vector Vj from our list B and let B now denote the list with the vector Vj removed. Okay, and what we're going to do on the other hand is if Vj is not in the span of V1 through Vj minus 1, we keep it in B. So we kind of do this for each vector, right? We do it for the V2, V3, V4. And if it's in the span of what we've seen before, we remove it. If it's not in the span of what we've seen before, we keep it. And so we just kind of move our way through. Okay, and now we only have to do this L steps. After L steps, we finish, right? Because we've looked at each vector. And what do we end up with? Okay, so at each step, okay, we have that the span of B is still V. And the reason that we're doing that is we're using our linear dependence lemma that we proved in a previous lecture. So when we remove things that are in the span, when we remove it, we're not destroying the span of the whole set. And we're keeping any Vj that we need in order to generate the whole vector space. So, and moreover, what we have left over is B contains only the vectors Vk such that Vk is not in the span of the vectors that you've seen before, the span of the vectors you've seen before. So the vectors left over are linearly independent. So we took a set of vectors that spanned. Each time we remove a vector, it still spans, and when we're left over, we're left with linearly independent vectors. And so as a conclusion, B is a basis because the collection of things in B is both a spanning set and linearly independent. Okay, so this is a very useful fact, and once you have things like that, you can prove something like this, namely that every finite dimensional vector, and I should put the word space there, has a basis. And why is that? Well, remember that being finitely dimensional implies that there's a collection of vectors, v1 through vm, that span v for some vectors v1 through vm. And now, by the previous result, some subset of v1 through vm is a basis. Okay, and so there we have that every vector space has to have, every finite dimensional vector space has to have a basis. So this is a very useful result, namely that you can start with a large list of vectors that spans your whole set and subtract kind of extraneous vectors to get a basis for your vector space. So we're going to pause here, and in part 3, we're going to look at kind of the opposite of this theorem.